Do you ever wonder how circuits work? And on top of that, how to trace those circuits so we can understand them better on the map. So let's look at simple circuits today. We have also components of simple circuits. We're going to see series circuit and parallel circuit. If you have any other questions about circuits, do not hesitate to ask your questions as we are going along. So let's see if we can do the first bit of learning. So this is a website called FET. It's from Colorado University. I'm going to put a link in the chat section here. I use it in class to do simulations, especially for people doing homework. Otherwise, in class, we always do hands-on activity. So here, I'm going to show you here in at the bottom here, the basic electrical circuit. So here I have a cell, so energy cell. So when you are looking at an energy cell, like Duracell, for example, Energizer, or any other company, these little cells are, let's see if I can put it there, they measure about 1.5 volt. So if I have here a voltmeter and I check, I should have 1.5 volt. So this is an energy cell. If you put many energy cells together, then you end up with a battery. A battery is great because you have more energy for the electrons to make something work in your circuit. So what we're going to do today, I'm going to put it about 9 volt. I think that should be plenty. Let's see, as a start. But as you can see, I can go all the way to 120 volts because there's also a simulation where you can actually use AC current. This one here is direct current. It works in your phone, for example. So we have an energy source. We have here conductors. We have here our first bulb. This bulb here is what we call the resistance. A resistance is a place where the energy of the electrons are being transferred from the chemical energy from the battery, and it's transformed. So let's see if I can close the switch. So here the bulb is transferring the chemical energy from the battery all the way to the bulb, and then it creates light. Resistance can create light, can create heat, movement like an electric motor, can also, what else could it, heat, light, and there's something else, and sound. Your phones have all of those things. And here we have electrons going this way, all the way back to get more energy in the battery. I remind you that I call this one a battery because I have, actually, let's put 2. So for me, this always looks like a cell. So I'm going to put it this way. I'm going to put 2 batteries. By putting 2 batteries, there you go, then 2 energy cell, I can actually say that it is a battery. So I'm going to put it like this, and let's put 9. So we have 9 volt here plus 1.5 volt. That gives us a total of 150. There you go. We have the electrons going around. The only way they can move is if the interrupter is closed. If it is open, nothing can move. So here the reason why the electrons are moving this way is that when we close the circuit, we have the electrons attracted by the positive end of the battery, and then electrons are located on the negative side. So what happens is that the electrons can now move and reach the positive side of the battery. At the same time, they go through the bulb, creating light. Now, this is what we call the movement of electrons. The conventional way to show how current works is the other way. I don't have a great explanation to why that is. All I can figure out is that if you have the negative end of the battery, maybe people say, well, that means that more negative are going this way. But that's an educated guess. If you know the answer, I'd be more than happy to know. So here, I like the way electrons are working, so we're going to put it this way. So here, I can see that I have 10.5 volt of energy given to electron. So that means that if I put, okay, so let's see if I can put the switch back. So what's happening here? I'm going to put the switch back. It's not happy, eh? Wow, okay. So switch on, switch off, perfect. If I go and put my voltmeter on either side of the bulb, let's see what number I get. I know that I have 10.5 volt here. If I close the circuit, the light bulb is on and I have here 10.5 volts. So that means that all the energy absorbed by this here will be given completely to the bulb right here. So let's see if we can look at how we can do the tracing of this bit. So we're going to look at some symbols. So first of all, we have wires. They're in a straight line. That's easy. We also have our source. So this is a cell and this is a battery. Often we like to say what is the voltage at these source. Another piece that is interesting is we need a switch. So this is a closed switch and this is an open switch. An open switch does not allow electrons to go through. A closed switch makes sure that the electrons are moving and therefore turning on the light. Something else that is useful, and we have the bulb. So this is a symbol for resistance. So here we have switches. This is a resistance. So resistance have several possibilities. They can be resistors where the only thing they do is to slow down the electrons. I'm going to show you a few different examples. So this is an example of a bulb. That's the one I've been using ever since I went to school. Some places in Europe, they put an X like this. Some other people, it's a line and there's a little bump where this is happening here. So there's different ways of showing how lights can be. I'm going to keep it like this. If some of you want more clarification on how these are, put the question in the comments below. I'd be more than happy to show you. So if I put back my circuit here, let's see if I can do the drawing of that simple circuit. So first of all, let's see, we have to here, from here to here. Perfect. So I have here 10.5 volt for my two cells here. I have a switch. And what happened here, I have my bulb. That is like this. Because I have 10.5 volt in this battery, 10.5 volt will be going through this bulb. Interestingly enough, we also can measure how many electrons are going through that place, through the circuits at one place. So here I have my ammeter, and if I put it here, I notice that I have 1.05 amps. If I go all along, at the bulb I have 1.05, here I have 1.05, and at the battery as well. And the reason is that there's only one way for the electrons to move, and that's why I have the same number all the time. So here, if I put here my ammeter like this, I would have 1.05 amps. So that's very good. Perfect. So now let's see what happens. So this is what we call a circuit, a simple circuit with one bulb. So I'm going to add something here at the top. I'm going to open my switch. I'm going to plug this one. So here we're going to have electrons that can go here in two possible ways. They can go either on the first branch or on the second branch. So here we have two ways for electrons to go. This is what we call a parallel circuit. So when I close the circuit, I can see that electrons are going either this way or they are going to the other branch. Now, interestingly enough, look at the light bulb. We have here a bright light bulb, but when I have two light bulbs, then they're a bit dimmer. So let's see if we can measure information here. So if I measure how much energy goes through the two bulbs, I have 10.5 volts. That's the same thing as the energy in that bulb right here. However, now the energy of the electrons have to be divided in two because we have two light bulbs. So if I go here, I will notice that the energy given to this light bulb is now 5.25. If I go on the other side, for this bulb here, I have 5.25. So that means that, oops, this way. When I have my energy going this way, I have 10.5 volt. So all the electrons going this way have 10.5, and going up here also have 10.5, but they have to divide the energy into. So let's see. On this branch here, I still have 1.25 amps because there's only one way and one bulb. However, if you go here to the other branch, I have now 0.52 amps. So that means that each of the bulb have half the energy, but the number of electrons going on this branch here is half as many as well. So interestingly enough, that means that 0.5 amps are going this way. We have 1.05 amps going this way. So that means in the whole circuit, here and in the battery, we have to add how many amps we have from the two branches. And therefore, we have 1.57 amps here. And I suggest that you use the simulation here to actually see the numbers to see how they work. If you have access to equipment and do circuits hands-on, please do so. And you'll notice that if you have one bulb compared to two, the two bulbs will be dimmer and you can measure the voltage and the current. It is amazing. So let's see if I can add this to the circuit we have here. So here we have another branch, first bulb, second bulb like this. Each of the bulbs is half, so we have 5.25 volt, 5.25 volt. We noticed here that when there's an ammeter, it's 1.05 amps. When there's two, it is 0.52 amps, which is half of it. And here we have the sum of all the amps so far, 1.5. So how much do they say? Just making sure it's 5.7. There we go. 1.57 amp like this. So here, what is interesting, we have a parallel circuit. So some of you will say, well, what is a series circuit? So if I was to take, so let's see. So this is a parallel circuit because the electrons here can actually go in two different ways. But if I take this branch off, the electrons here that has to go through two resistance, two bulbs. Here, this is a series circuit. Series means that the bulbs are one after each other. When it's parallel, there's two different ways for the electrons to go through. So that is the point here. Let's see if we can go and add a third branch to our parallel circuit. So here, what I'm going to do, I'm going to put this one here and this one right there. And I'm going to close my switch. And what do I have? I have here my three branches. First branch here has a bright light bulb. This one here, I have two dimmer light bulb. And here I have three bulbs. And as you notice, the three bulbs are very dim. And the reason for that, if I am to look at the measurements, the number of volts in that bulb here is 3.5 volt. For the next one here, 3.5 volt as well. And for the next one is 3.5 volt. So here somehow the energy of the electrons are divided. So if I have two bulbs, 3.5 plus 3.5 is 7 volt. And if I include the three of them, I have 10.5 volts, which makes sense because when we have here the electrons going through the battery, each electrons are gathering 10.5 volt to give their 10.5 volt to one bulb. That means that the bulb has the whole 10.5 volt. And you go here, the 2 volt are getting the full 10.5, but because there's two, we divide the voltage. And here in the third branch, the electrons do have 10.5 volt as a whole because that's the total energy they have, but they have to divide the energy. So each of the bulbs have 3.5 volt. Now that's the first thing. Next one, let's see what else we can say. So here, if you take that one branch only, that this is one branch in series. So these bulbs are connected in series. The current, if you have one bulb, is 1.05. We saw that earlier. If there are two bulbs, they're divided in two. So 1.05 divided by 2 is 0.52. And if you have three bulbs, what do you notice? It is even slower. And as you can see, the number of electrons, they are slowing down as well. The current here is 0.35. That means that you have electrons that have three ways. So we have this first branch, second, and third. So here we have a total of 1.92 volt going through the whole circuit. So every time you add a branch for the parallel circuit, the current here keeps getting bigger and bigger. So what happens if I keep putting in information? So I keep putting volt, I keep putting volt. That means that there's more energy here. The batteries can take more and more energy. But if you notice, look at the battery. I go from here and oops. So you get to a situation where there's so many electrons going through in this part right here. So only 9 here, 4.6, and 3.07. Each of the branches are manageable, but if you add them, then you end up with so much current going through that it is creating extra heat, and therefore this is an issue. How can we do this? Well, there's a few things we can do. We can either add resistors to intentionally slow down the electrons, or we need to put safety procedures here, for example, a breaker or fuse, to make sure that the circuit is protected. And that is, so here I'm going to see if I can create less energy. So I'm going to go here with 11 volt, and here I'm going to go down to 11 volt. Perfect. And now it's so much more manageable. So sometimes you're wondering if you have a phone. Let's see if you have a phone. If you have a phone, how come I don't have more power and more stronger, like a stronger battery? The issue though is that you can have stronger batteries, but you still have the circuitry in your phone that can take so much energy to make it work. There's been times in the past where phone companies had to discontinue phones because you were connecting them, and then the battery would burn, and then you had phones that were not safe, or phones that were very, very hot because of how much energy were going through the battery here and in the cell phone. So when you think of electronics, you have to be careful. Now, this is for direct current circuits. Now, in a house, for example, we have alternative currents or AC current. The voltage is at 120 or 240 volts in a house. We have much bigger wires. We have much bigger appliances. And if you go into the industry with the electric motors in a manufacturer, then again, what happens is you need safety features to protect your circuits, to protect your workers, to make sure that everything works out. So that is the key portion of what I wanted to do today. And let's see my circuit. And I think that's very good. So that's an excellent review on how we can work with parallel circuits with series circuit segments in them. I use the voltmeter, the ammeter to measure the current. I think that's an excellent review.